Imagine you're an alien who just landed on Earth. You hear humans making sounds with their mouths. The cat sat on the mat. What does this mean? How do you decode intent, emotion, grammar, context from mere vibrations in the air? This is exactly the problem computers face. Language isn't just words, it's meaning, nuance, sarcasm, metaphor, cultural context, all encoded in symbols we call text. Natural language processing, NLP, is teaching machines to understand human language. Not just recognize words, but comprehend meaning. It's why you can talk to Alexa, why Google translates 133 languages, why ChatGPT writes poetry. And in the next 5 minutes, you'll understand how it works, from tokenization to transformers, from word embeddings to attention mechanisms, and why this technology is reshaping human communication itself. Computers don't understand words, they understand numbers. So the first step in NLP is tokenization, breaking text into pieces that can be numbered. The simplest way? Split by spaces. Hello world becomes 2 tokens, hello and world. But language is messier than that. What about punctuation, contractions, compound words? Is New York 1 token or 2? Is don't 1 word or 2, do and not? Modern NLP uses subword tokenization. Instead of splitting by words, we split by meaningful chunks called tokens. The word unbelievable might become unbelieve-able, 3 pieces. Why? Efficiency. English has over 170,000 words, but with subword tokens, we can represent all of them with just 50,000 tokens. New words? No problem. We build them from pieces we already know. Watch how a sentence gets tokenized. Each piece becomes a number. And those numbers? That's what the neural network actually sees. Now we have numbers, but they're arbitrary. Token 5496 for hello has no relationship to token 3303 for world. We need to give these numbers meaning. Enter word embeddings. Instead of a single number, each word becomes a vector, a list of hundreds of numbers, positioned in a high-dimensional space where similar words are close together. Think of it like a map. King and queen are neighbors. Paris and France are nearby. Happy and joyful almost overlap. The geometry itself encodes meaning. Here's the magic. Vector math works on meaning. King minus man plus woman equals queen. Paris is to France as Tokyo is to Japan. The relationships are captured in the geometry. How do we create these embeddings? We train a neural network on a simple task. Predict the next word. Show the model, the cat sat on the blank and it guesses mat. Do this billions of times on billions of sentences. The network learns that cat, dog, and mouse are similar. They all appear in similar contexts. That similarity becomes geometric closeness in the embedding space. This is the foundation, words as vectors, meaning as geometry. But there's a problem. Words don't exist in isolation. Bank means money in I went to the bank, but means river edge in I sat by the bank. We need context. We need to process words in sequence. Enter recurrent neural networks, RNNs. An RNN reads text word by word, maintaining a hidden state, a memory of what it's seen so far. Process the memory. Process cat, update memory. Process sat, update memory. By the time we reach mat, the network remembers the entire sentence. This hidden state is like short-term memory. It carries forward information from previous words. The network can now understand context, grammar, long-range dependencies. But RNNs have a fatal flaw. They forget. After 10 to 20 words, the memory fades. Try to reference something from 50 words ago? Impossible. The vanishing gradient problem kills long-term memory. This limitation held back NLP for years. Until 2017, when everything changed. Then came the paper that changed everything. Attention is all you need. The transformer architecture. Instead of processing words sequentially, transformers look at all words simultaneously. They use attention, a mechanism that lets each word look at every other word and decide what's important. When processing bank in I went to the bank to deposit money, the attention mechanism looks at deposit and money and concludes financial institution. In riverbank, it looks at river and water and concludes land next to water. Here's how it works. For each word, compute 3 vectors, query, key, and value. The query asks, what am I looking for? The key answers, what do I represent? The value contains, what information do I have? Attention scores, how much query matches key. High score, pay attention. Low score, ignore. Then we take a weighted sum of values. The result, each word gets a context-aware representation. Stack 12, 24, 48 of these attention layers. Add billions of parameters, train on trillions of words. The result, GPT, BERT, ChatGPT, models that can write, reason, and converse. Transformers don't forget. They can handle 100,000 word contexts. They parallelize beautifully on GPUs. They scale, and that's why they dominate modern NLP. So what can we do with this? Machine translation. Google Translate uses transformers to translate 133 languages in real time. Attention learns alignment, which source words correspond to which target words. Sentiment analysis. Amazon, Twitter, Netflix, analyzing millions of reviews to understand customer emotion. Is this review positive or negative? NLP decides. Question answering. Ask Wikipedia a question, get an answer. BERT powers search engines, extracting relevant spans from documents. Text generation. ChatGPT, Claude, Gemini, generating human-like text. Creative writing, code completion, conversation. Named entity recognition, extracting names, dates, locations from text. Used in law, medicine, finance for document analysis. And the future? Real-time speech translation. AI tutors that understand your questions. Medical diagnosis from patient notes. Legal document analysis, all powered by NLP. But NLP isn't solved. Challenges remain. Bias. Models trained on internet text inherit human biases, gender stereotypes, racial prejudice. If the data is biased, the model is biased. Interpretability. Why did the model generate this? We don't fully know. Attention helps, but these are still black boxes. Common sense. Models can write essays but fail at basic reasoning. How many eyes does a horse have? Easy for humans, hard for models without real-world grounding. Multimodal understanding. Language isn't isolated. We need vision, audio, touch. Future models will be multimodal, but the trajectory is clear. From tokenization to transformers, from word embeddings to attention, we've taught machines to understand language, and that changes everything.